speaker, please. So Sebastien Tavenas is going to talk about optimal depth reductions for algebraic formulas. Joint work with a lot of people, Sebastien, Nathalie, Guillaume Maillot, and Shrikant Srinivas. Sebastien.
Hello. So thank you for attending this presentation. Thank you very much. So I will present some work I did with a lot of people. So with Hervé Fournier and Guillaume Maillot, who are in Paris, and with Nutal Nimai and Shrikant Srinivasan. So Nutal Nimai is in Copenhagen. Shrikant Srinivasan was in Aarhus, and I don't know if he's already, or I think for from the next year he will be also in Copenhagen. Okay, I didn't do that. So we'll talk about algebraic circuit, in particular algebraic formulas. So algebraic circuit, it's a model of computation. We want to compute a polynomial. So we want to do as in Boolean, but instead to do and or, we'll do addition, multiplication, subtraction. So at the bottom, we put the variable or constants, and we do arithmetic operations. So mainly on a circuit like that, we consider two parameters for saying is this model complicated or not. We look at the depth, will be the path, the length of the longest path, and it will be the size. So for a circuit in general is the number of nodes, for example, it's here 11. And in particular, today I will be more interested in formula. So formula is a circuit, so just the underlying graph is a tree. So the formula is more something like that. So we now still have the depth. In general, now the size of formula, we mainly count the number of leaves. And so here it's a 16. We can always go from circuit to formula by expanding everything. It has a cost. The cost in general, so it will be the size to the depth. And something which will be interesting for us is the last line, which is a bit below here. It will be, we'll consider homogeneous formula particularly. So in fact, if we want to compute a homogeneous polynomials, maybe at some point in the intermediate, we can compute something which is not homogeneous. A homogeneous formula is a formula such that at every gate, we compute only homogeneous polynomials. So we can look at this formula. Normally, it's homogeneous. We compute only gates of degree exactly 1, homogeneous polynomial degree 1 at this layer, always degree exactly 3 at this layer, and we do the sum at the top. Okay. So the main question in general in algebraic complexity theory is the same as in Boolean. We would like, the dream, it will be to get superpolynomial lower bound against algebraic circuits. So maybe already you can be less picky. And we say, oh, okay, we are already it's good if we can get something against formulas. Okay, and we had a recent result with, 2 years ago, with Nathalie and Shrikant Srinivasan. So we showed that, in fact, we can get superpolynomial lower bounds against constant depth algebraic formula. A bit what happened for Boolean. We know in the constant depth setting, we can get superpolynomial lower bound. In fact, if we want to look at more precisely in the proof, we can look at until which depth we can still get something. And in fact, the proofs still work until a depth which will be log d, where d will be the degree of the polynomial computed, everything like that. And we also need the condition that the degree is really smaller than s. Okay, but so now it's a question. It is if we start with a polynomial with a small circuit, maybe you can sum parallelize until which depth, because that would be really dreaming. But if we can parallelize directly any small formula in depth log d, now we will get general lower bounds against formulas. So the question is until how much we can parallelize a formula. So what we know about parallelization of formula? So there is the first result by Brent, Kuk, Maruyama. So it's a bit similar to people in Boolean, the Spira result. So that if you have a formula, a small formula of size s, and you can always parallelize to depth log s, and it's a polymer size. There is another result after, which was a very big thing in algebraic complexity because it's something which really looks wrong, not correct in Boolean complexity. The result by Valiance, Kuhn, Berkovits, Serakov, which are saying that if you have a polynomial which is computed by a small circuit, you can compute it in, with a small circuit, still poly size, and now with the depth, it will be log of the degree. So we can, if you have a small circuit, you can always parallelize in algebraic complexity, in general, a small circuit to log degree. Okay. And something which is a bit strange here, it seems that we have something which is better in some way. If we are coming back to the regime when the degree is really smaller than the size, we are computing a polynomial of low degree, for example, of degree square root of n, and we are working with a polynomial of set n, or even we are computing a polynomial of degree log of n, where n is the number of variables. It seems that we can get a depth which is really, really smaller for circuits than for formula. And in fact, yes, this is true. We don't know. We don't know if there is a way to compute any formula in depth log d. Now, what we can say? We can still say something. Once I said before, in fact, we cannot use the result for the circuit, which is stronger for formulas, because what we get after the reduction of VS barrier is really a circuit. Even if we start with a formula, by doing this reduction, we'll finish at the end with a circuit. And now, if you want to get back to a formula, you will need an exponential size blow up. Okay, but we know some things. We know some way when we can beat the reduction for BKM. Our first things, in fact, I didn't say something we show in the beginning. Here, in general, fan-in, when I say nothing, it will be unbounded. If I want to get something of log d depth, for example, if I just take the sum of the n variables, the degree is 1, I cannot up by fan-in 2 to get something in a constant depth. So we'll mainly work with unbounded fan-in. In fact, something we can notice, if we are working with a polynomial with a small sparsity, already you can get very good reduction, depth reduction. That is maybe a trivial case, but if you have a few monomials, you can just write your polynomial as exponent, as a sum of the monomial, which will be a depth 2 polynomial, so really a dream. And in fact, we can notice that in some cases where, in fact, we know we can already beat the first bound. For example, if we are working with a really low degree polynomial, when the degree is logarithmic, at most logarithmic in the size, in fact, there is a result by Randraz in 2013, where he showed that in these settings, when the degree is very, very small, in fact, we can homogenize a formula in a poly size. So if we start with a formula, maybe not all get intermediate homogeneous, we can, in fact, homogenize it. If we compute something which is homogeneous, we can homogenize it in poly S. Okay? So if we do that, in fact, we can notice now if we have a homogeneous formula which computes something of degree d, and now, in fact, you can merge the sum and the product. So you will get product at each layer. You can get at most d product in your computation. So the depth will be at most d. And in this setting, this is already smaller log s. So we are already beating the bound by BKM. Okay, but this is still big O of d, which is really larger than what maybe we'll be doing. So in fact, we show two things. No, we show one thing. In fact, the second thing is mainly a corollary. We show that, in fact, if we are working with homogeneous formula, we can parallelize them to log d. That we'll see after. There is a corollary from what I exactly told you before, the result using Randraz result. If we are in the setting where the degree is really small, smaller than log s, in fact, what we can do, in fact, each connected component, we can homogenize it using this Randraz result. Now we have a homogeneous formula for each connected component. We use the first part. We do a log reduction for all homogeneous components, and we get at most big O of log d formula, the log d depth formula for your initial polynomial. So the result shows that we can do it for homogeneous formula. We can do it when the degree is very small. It's still open if we can do it for all formulas, all small formulas. Okay, so we can say what is the intuition of doing something like that. Maybe the idea is to look at what will be intuitively will be the hard case. So first, before to look at exactly that, we can notice something quite easy. If we look at only the multiplication gate, and if we assume the multiplication, yeah, yes? Bigger of log if, yeah. If d is a smaller of log s, in fact, by Randrad's result, we can homogenize it. As soon as it is homogenized, we can use the first point to do a small depth formula. Okay, so in the multiplication, if for all multiplication gate, we assume that, so if we have a homogeneous formula, we can associate to each gate a degree, because all monomials are exactly this degree. And if we assume that for each have a multiplication gate, all children have a low degree. By low degree, I want to say the degree is half. In fact, if we have that already, it will win. That will directly obtain something such that the depth will be log d, because the same, we will be able to merge the plus and the product gate, and each time we do a product gate, we divide the degree by 2. It can be at most a log d steps. So in fact, the problem, if you want to get a hard case, it will be when we have some children of a multiplication gate such that the degree is large. And we can already notice something. For each multiplication gate, there are at most one child such that the degree is large. We are working with homogeneous polynomial. So in fact, the sum of the degree of this gate is exactly the degree of this gate. So the number of children such that degree is at most half with at most 1. So in fact, particularly, that's quite interesting. Roughly, the only thing we need to fix a formula to make it log d depth is to look at what happens when a child of a multiplication gate has degree more than delta d by 2. Okay. So with this intuition, you can say, maybe we can try to make what will be a hard case. Our hard case, what will be, for a plus, I have no restriction. After we look at multiplication, I want to get a very large child. So what I do, I put each multiplication one variable on one side, and a formula on the other side, which will be of degree, the degree of the gate above minus 1. I just decrease the degree by 1 each time I have a multiplication gate. This is really what will be the problem. But in fact, this case is a very easy case. If someone noticed. In fact, the sparsity of this polynomial will be smaller than the number of leaves. So this polynomial is sparse. As my trivial example before, sparse polynomial, we can reduce them in small depths, even depth 2, just by expanding them. And that mostly should be the idea. What will be the hard case? We will look at when we have a product, what is a large sum, and look at things like that, or something sub-tree around that, and we want to expand them. We want to say that cannot be too large, and expand them, and to plug all these things together. And that will be roughly the idea of the proof. Now we can try to see more carefully the proof. Okay, so what we can do, we can start from our formula. So we didn't put here, but the first thing we can do, we can already apply the BKM depth reduction. So we start with a formula of size s, and with a depth at most log s. Okay, and we'd like to add a potential value to each gate. What is the intuition of this potential value? It will be at which layer it will be placed in the final formula. So we want to put some value, associate already the final depth in the final formula of our initial gates. So what we see here for gate alpha, we'll put particularly the main point, the log of the degree of this gate. In particular, each time the children has a degree at most the half of the parent. If there is a child has a degree at most the half of the parent, this will decrease by 1. And so it will be below in our formula. So if you are looking only of a formula which will be at the same layer at the end, this value does not change. In particular, it means that the child is a large gate. And we need to add another constraint. In fact, this one will be useful, otherwise to maintain the size not to be too large. We'll see after. Okay. I claim something. I claim that, so if we start with a formula, you do this potential function. If you start with a homogeneous formula of fan in 2, so I didn't say nothing, but in fact, if we start with a homogeneous formula, you can make it fan in 2. That doesn't change the size. It changes the depth, but already at the beginning, the depth, we do nothing. We use became depth reduction. It will give us something of fan in 2. So let's start. It's easier with something of fan in 2. Depth delta and size S. And assume, lemma, from now, that we can transform into a formula of depth product depth. For me, it will be the product depth. So product depth is just I look at the number of multiplication in the past. Which will be at most, so the potential value of the root. I say I want to put a product for each different values of the potential. And the size will be at most S to the 2 to the K log D. That will be the blow-up inside I will allow. I just want to show first why, if I have this lemma, is this finished. Okay, let's choose K equals log S divided by log D. The depth we saw, this is the potential of the root. The potential of the root, this is log D. And this is sum of depths. This is at most log S, since we start with something which is already in depth log S. And this is log S divided by log D. So this is also log D. So using this thing with a K equals this thing, the depth here will be log D. And the size, what will be the size? We have S times something log S divided by log D times log D. It is log S. 2 to the log S, it is S. So it will be size S squared. So if we can get the lemma, we'll get the main result with a G, no. G. Multiplication, addition, from now it will be unbounded. But in fact, what you can notice, I will need to say that after, that in fact, posteriori, you can make the fan-in of the multiplication gates too, constant. So you can do it. I will not show it now, but I will just say it after. Okay, so I say we want to do this from our initial formula. Okay, so what I say we start with our formula, and we want to look at all the gates in one connected component, which has exactly the same potential. So in fact, what we can notice, a connected component of the same potential is something like that. What I say below a multiplication gate, there are at most one node. Below multiplication gate, there are at most one node, such that this doesn't decrease. So below multiplication gate, there is exactly one node, at most one node, such that the potential doesn't decrease. Okay, I put variable for things which are outside lower potential gates. Okay, and it's fan-in, so plus it's fan-in 2, things like that. And in fact, we just recognize what we had before. We get something which is also a skew formula. By skew formula means that each multiplication gate has one child which is variable, and the other child is the rest of the subformula. Okay. And we know also something else. We know that in fact the depth of that is at most k. Well, 2k. Because we know that if when the sum depth will decrease to k, the sum depth will be more than k. In fact, this value will decrease. So it will be something which is a lower potential. Okay, so this formula is skew. So we know, in fact, this is a sparse. In particular, we can write it as the sum of product, and the number of, we say the sparsity, it will be smaller than the number of leaves. The number of leaves here is a fan-in 2 formula of depth k, is at most 2 to the k. Okay, so now we'd like to, to connect this formula to plug them. But something we can notice that when we transform that into a depth 2 formula, we'll need to duplicate some leaves. So we need to be careful how many times the leaves are duplicated. But in fact, not that too much. There are different leaves. In fact, we can notice the leaf here, for example, is not duplicated. sorry, this is the opposite. The leaves which are completely below, I didn't draw them, they are not duplicated. This one can be, but this one cannot be. In fact, this will be, if we do the depth2 formula, it means we'll expand all the subs, so we'll multiply this variable to this subtree and this subtree, so it will be multiplied in different monomials. But leaves which will be completely below, there will appear in only one monomial. In fact, we see monomials by one pass in the tree, so leaves which are completely below the pass appear in only one monomial. So the only leaves which are duplicated, they are exactly the leaves which are below a multiplication gate. They are exactly the leaves such that this decrease. In particular, if we look at in the initial formula, a leaf is duplicated only when it appears in the path such that the degree is multiplied by 2. So in the whole formula, each leaf is multiplied at most 2 to the k times at each step, and the number of steps can be at most log d. So the maximal number leaf at the total will be duplicated. It will be 2 to the k log d. In particular, so putting everything together, we'll get normally the lem at the top. We start with the formula of set S, and we duplicate each leaf at most this number of times, which will be the final formula. Okay. So we prove that we can parallelize homogeneous formula, and so we can get a corollary when, for all formula when the degree is very small. Exactly the thing I said before. In fact, we can notice something. Even when I state it like that, I can put finding 2 everywhere in the final statement. In fact, first, we can, a posteriori, get a multiplication to get finding 2. In fact, we just want to get log d, and plugging multiplication is not a problem. After the problem of addition, but when I started it like that, here I started it with product depth. So if you just consider product depth, you can also make the finding of the addition get 2. We don't change the product depth. So set it like that, we can get finding 2 everywhere. Or otherwise, you can look at depth and you have finding 2 only for product multiplication gate. This transformation, in fact, it preserves roughly anything because it was quite final sample. It's just reorganizing how the computation is done, but we change nothing about the computation. So it preserves monotonicity. By order, I want to say if we have a multiplication, we preserve the order of the children. Even same for addition, but in general, it's not really important. Alternative. We show something that I didn't want it to present because it's more technical. In fact, it's not that interesting. In fact, so it preserves everything. So it's true in the case of monotone formula. Monotone formula is when we don't allow subtraction. We only have a positive constant, addition, multiplication. In general, we have a lot of lower bounds in this case just by looking the support of the polynomial. It means which monomial appears in the polynomial. And in fact, by doing exactly a lower bound like that, we can prove that we can not beat. There are polynomials, there are formula of depth log d that we cannot compute them polynomially in depth less than log d. And one last thing, in fact, we can show that we can, in fact, there were some results, some improvements that became results, that not really improvement, it's not really comparable, but it shows that if you want to get the depth reduction such that we don't allow poly-size transformation, but we just allow near linear size transformation, what depth can we still get? And we can do that, in fact, using this thing first and doing something similar, we can get a reduction to depth log to the 1 divided by epsilon log d. And the increase in size will be only s to the 1 plus epsilon. One thing for people who notice, in fact, I don't know, in fact, we use very few things about homogeneity in this proof. We say mostly nothing homogeneity. What we use, finally, for homogeneous formula, we use the fact that we have a degree of for the different gates. So we have a function for each gate, we associate a degree. And the only thing, grossly, we would like to get to that is only one child can get a large degree. And to the potential function, we would like that this degree is monotone. It increases along the formula. And in fact, we have a syntactic degree. In general, sometimes if we are working with a formula which is not homogeneous, what we say in general is called a syntactic degree. We put 1 for the variables, 0 for the constant. When you have an addition, you take the max, and you have a multiplication, you take the sum. It will be what we call the syntactic degree. And in fact, as soon as the syntactic degree is bounded by a poly D, in fact, the proof works. Okay, so to finish, I just wanted to mention some strange things, or I don't know if this is strange things, but funny things, I think, which are coming about that. So in fact, we can show that, so what we call in general, I wanted to put VF, sorry. So small polynomials are computed by small formula, which is in class, which is we in general call VF. So in fact, inside this class, so we have what we can compute by small homogeneous formula, which is in particular case that what we can compute by a small syntactic degree small formula, because if you have homogeneous, you know the syntactic degree is exactly D, so more, it's really poly D. In fact, in this paper, what we show that this class, when you have small polysyntactic degree, in particular, we also have a low degree. When I say low degree, I want to say degree at, low depth. When I say low depth, I just want to say the depth will be logarithmic D. And we can question, are this class equal, distinct? How far will be in this class? It's not completely obvious, I think. One thing is a bit funny, in fact, there are a lot of things. For example, if you look at Randra's result, not at all Randra's result. There are different results when we want to homogenize the formula. So to go really to the top at the bottom. The idea in general leads during the multiplication gate to compute the homogeneous components. And for doing that, in general, what we want to do, we want to compute elementary symmetric polynomial on the entries. So to put something, to go from here to here, in general, we want to compute homogeneous symmetric polynomial, elementary symmetric polynomial. And it's quite fun because where, in fact, are these polynomials? In fact, by a result by Ben Orr, we know that we can compute them by a low depth formula. And in fact, there is also a result by using Newtonian entities by Spilka and Ingerson, so that we can compute elementary symmetric polynomial even by depth 6 small syntactic degree formula. And it's completely open to know if we can really compute them in this polynomial or not. In some way, it seems that quite they are in some way complete in the way that probably if we can compute them like that, probably all the class, we don't really have a wrong reduction, they say, in general, it's the polynomial we try to use to homogenize. So, okay. Thank you very much.
We had some questions during the talk, so thank you so much again.
Thank you very much.